If we have a binary tree, how to print a left view of it? This is a popular interview question in Microsoft, Google, Amazon, and so on. Today we're going to solve this problem in Haskell. What is a left view? To understand this, look at this picture. I think it is very intuitive. So you can see here the red nodes represent the left view of the tree. So imagine like we have a vertical line here and it moves from the left to right, and each node at every tree level which we pick up at first will be in the left view of the tree. Okay, here we have a binary tree definition with this polymorphic data type. By tree, it takes some A, and the tree is either empty tree or the node, which have a left subtree and the right subtree. I'm using this model pretty tree, which allows me to print the binary tree. I want to visualize what we are doing. Actually, this data type defined in this model, but I copy it here so we can see it. So let's look at some tree. I have some tree defined, and let's pretty print it. So look at this tree. It has some paths in it. So if we take all the paths of this tree, we can somehow combine them and receive our left view of the tree. You can see that this is the first path, A, B, and D is actually it is the left view of our tree, but possible that this is not only the this is not the final solution. If our tree was another form, for example, if we have some branch here, this is leftmost path, it will be only the part of our solution. Also, we need to pick up some longest paths from here and so on. But this path is somehow like mask them from the left. Okay, let's start to implement this. First of all, let's implement the function. I will call it paths, and it takes some battery of A and produce the all possible paths from the root of this tree to all the leaves. And let's start from some corner case. Then we have an empty tree, then we have no paths. This is an empty list. And if we have some tree constructed with the node constructor and some left and right subtrees. In this case, what we need to do, we need to take all the paths from the left subtree. This is a list, so we can concatenate it with all the paths at the right subtree. And now all these paths need to start from our A node, okay? Because here all the left subtree paths. So in this case, this is B, D, B, E, C, F, and C, G, and all these paths must have at the head A node. So we need to map it. here with our A node, like this. And now we need to add some one case. Then we have a node, the leaf node, with empty subtrees. In this case, our paths are only one node. We have only one path with this one node. Let's try to compile this thing. I will load my file here. Okay. I think I need parentheses. And it compiles. And now let's look at our tree again and try to build all it with its paths. And paths. Okay, we can see that we construct list of all the paths. Now I need to implement some helper function which do merging of these paths in mask. I will call it mask merge. So mask merge, and it takes two lists. Actually, in this case, we take this list and this list, and it must build a new list. It starts from the list X, and then we drop the number of elements in the list X from list Y, from list Y, sorry, and the other part of it we need to concatenate that list X. So let's check how this function works. Sorry, like that, I think. So let's check how it works. If we have some two lists and one of the list is greater than and the second list is greater than the first list, when we take first elements from here and the tail elements from here. Here they have only one element because one list 1 to 3 is masked. This list here, it masks 4 with 1 and 5 with 2 and 6 with 3. Now, when we have all these paths of our tree, we can merge them using fold alpha function. So now we can implement our left view of our tree. It will looks like this. We take our fold L function. We take our merge function for folding, mask merge, and they take empty initial list, and then in the end they need to take all the paths of our tree, and this will be the solution. So let's reload and try to left view of our TR, and we can see that this is ABD, and this is correct solution, because if we looked from the left here we will see ABD. But let's look at some more complex tree. Okay, I have some tree looks like looks like these. No, T T R. TRR, I think, yes. TRR. And you can see it have some complex structure. And now let's try our function on this tree. Okay, we have a result, and let's look at this. A, B, C, D, F, X, A, B, D. Okay, it's correct result. And now, let's build the right view of the tree. Okay, we can build it exactly the same. We have some tree, but now we're using the fold R function, and we need to flip our mask M function. And initial list is empty, and we need to take all the paths. Let's recompile and let's try to view right view. Okay, this is how it looks. Let's print out array again. Okay, A, B, C, D, F, X, A, C, G. Okay, the right view is also correct. But now let's check our program in such more complex tree. If I add here some small right subtree, and we can see from the right, will this node mask be? Okay, so to do this, I need to take my TRR tree and construct a new tree with node. I think it will be node Z, and our TRR tree will be from the left, and from the right we will build one node. Okay, this is a node. Node V, and it have two empty subtrees. So let's try to define it as tier2, and now print it our tier2. So, and now let's check right view. Will it handle this case or not? Right view of tier2, and we have ZV. So we see that our V masks our A, and then we have B, C, D, E, F, X, A, C, G. Okay, this is works as expected, and I think this is a correct implementation. Of course, I think it is not very effective, but it works. Okay, now let's try to do something more effective. And to do this, we need at first implement the level order traversal with zip function. So to do this, I will define a function LO, level order, and its type signature. It's take binary tree of type A and produce a list of lists of type A. So these inside lists are labels, And let's start with corner case, then they have empty tree. In this case there is no levels and we return the empty list. But if they have some node with A and left and right subtrees, in this case how we construct levels? Okay, here we will have one top level with one element A, and also we can take levels of left subtree and levels of right subtree. Okay, and they need to zip them. So this thing will be list of lists and this thing will be list of lists, and they need to zip these two lists, and they need to concatenate the inner list, and we will do with the zip prime function. Okay, and then they do this, we need to add also this top level at our result. So one final step, we need to implement zip prime function. Okay, let's start to do this. We start from type signature of this function, take a list of lists and another list of lists. The inner type is same and it produces a list of join lists. So let's start from some corner cases. If we have left list and empty right list, in this case we just return the left list. Otherwise, if we have empty left list and not empty right, in this case we return right list. If actually left and right can be also empty, but it doesn't matter. Here we must return the not possible not empty list. So, and last case, if we have some not empty lists which we can unpattern match. So here we needed first to concatenate our inner elements, corresponding inner elements starting from the head of the lists, and then they need to add this thing to our recursive call with tails. So yes, our recursive call will concatenate again our heads, and in some point we will come to these cases and they will work. And I think this thing should work. Let's try to reload and try to test our zip function with some lists of lists. For example, like these 1, 2 and 3, 4. Okay, and you can see that it concatenate corresponds elements. So for example, we have such thing, it will work as expected. And this means that our level order traversal should work now. Let's check this. Okay, I will reload and call our level order traversal with our tree tier. And you can see this tree and its levels. Level A, level B and C, and level D, E, F, G. So, how can they now take the left view of this thing? It is very simple, I think. Left to U. We can define this function now, left to U. And it's take tree, and we take level order of T. We get this thing. And to extract the left view, we need to fmap this thing with head. Okay, we take only the first element of sublists, and let's try to check this thing. Okay, you can see that it works. And now let's define the right view also. If they have tree, it works exactly the same, but we take the last element here. And now try to check this. Okay, and you can see that it works. Okay, now let's use some more complex tree. TRR, the tree of this complex structure, and let's check our LVV prime with this tree. Okay, left view A, B, C, D, E, F, X, A, B, D. Okay, it works. Right view A, B, C, D, E, F, X, A, C, G. And it also works as expected. And now let's try the more complex thing to tier 2. I will show this tree. It's look like this, and let's try to check right view. Okay, ZV. Okay, B, C, D, E, F, X, A, C, G. Okay, it works as expected. So guys, this is all. I think the two ways of implementing left view and right view in Haskell. I hope you like this. Push like button, push subscribe, write comments, and see you in the next video. Bye bye.